Okay, it is 4 o'clock, so we shall begin. We're very pleased to welcome our speaker today, Christopher
Verhaaren.
I did try, but it's much better to have him do it. I asked him before today's talk what would he like included in his introduction, and he gave me the very modest but not so useful answer of nothing specific. He did just tell me he used to be the mouse at Chuck E. Cheese, so I thought that was an excellent achievement in his class. Originally from Chicago, he attained his PhD from the University of Maryland in particle phenomenology, which I thought was a phenomenal term to use today, and joins us today as a postdoc from Davis. So let's give our speaker a warm welcome.
So thank you very much. It was a beautiful drive up here from Davis. It's my pleasure to be here. I should say I'm not invested in finishing my talk per se. I care more about you guys feeling like you came away learning something. So feel free to interrupt, to ask questions. This is your talk more than mine. I've already seen it. I don't care. So if on slide 2 you have a question, raise your hand, because if you have a question on slide 2, probably slide 3 will be a problem. Might as well, stop at slide 2 and figure things out, and we'll go from there. But I do want to tell you about the Higgs Boson and kind of the fun detective work that's going on there. So let's see if I can go in the right direction. No. Yes. Good. So why am I likening particle physicists to detectives? Well, when you think about great detectives, what do they do when you read about them or watch them? One thing is they're tied to the evidence. They follow the evidence wherever it leads them, whether they like it or not. They often have kind of specialized tools that help them have some kind of advantage or special insight over others who might not. They typically have to sift through a lot of information to find out what's actually important to the question that they're trying to address. They have to use imagination, they have to use creativity, they have to posit maybe a lot of different ideas before they find one that fits the facts. And maybe the first one that fits doesn't fit the best, so they have to find a new one. Yes, in the back.
Please define important.
Please define important. It certainly is. I would say important depending on what kind of question you're trying to solve. So many things are, I guess, subjectively important, but if I'm, let's say, if I'm trying to find my daughter's favorite color, then I don't know. The important question to ask is to ask my daughter what her favorite color is, maybe. And but there's a lot of other information out there that becomes the important piece of data to that question. Does that help?
Yes.
All right. So particle physicists, they have a kind of a parallel set of things they deal with. They have to follow experiment, no matter how much you like your favorite theory. If it doesn't agree with experiment, it's wrong. Often there are specialized tools employed, whether experimental or theoretical. You have to know kind of the standard understanding, what we call the standard model of particle physics, very, very well if you want to get hints of things beyond that standard model. You have to use imagination, you have to use creativity to see how new data might answer old questions, or how to think of old questions in a new way. And you have to explore a lot of different ideas. There's no use being tied to one particular idea, because you might find out that it's wrong. And so you might as well try to stay broad and include all the ideas that you can. So as we know, the evidence decides. And here are some evidences that are out there. You guys have already, I heard about LIGO, and so you can see that the exciting evidence they found there of gravitational waves, direct detection there. Some are searching for dark matter in mines deep underground. Some are looking at the background sky in very, very careful ways, or watching for neutrinos that fly through polar ice. We're using all these very important and interesting experiments to try to understand the world around us. And the idea is to get as much data as we can to understand these and test the ideas we have against them. And hopefully the new data will help clarify, or at least make the non-clarifications sharper, so that we know what needs fixing. One tool that I'm going to talk about, one piece of evidence gathering, is the so-called LHC, which stands for the Large Hadron Collider, which I hear was prepped for you last week, so that's exciting. Here it is. Isn't that nice? It's about 27 kilometers around. It It didn't quite fit in Switzerland, so it bleeds into France. It's about 100 meters underground. It has protons, which I've colored red here, that fly around this ring very fast, and they collide at 13 TeV, which I'll explain what that means in a second. The pipe that they're flying through is very cold, 2 Kelvin, which is a little bit colder than space. How many times do these collisions happen? They happen about 1 billion times a second. There's 1,000 magnets, 10,000 magnets rather, about, and they're all 8.4 Tesla, which is a lot of Tesla, for those of you keeping track. It's a pretty intense machine. Why do we have this big machine that's at all the extremes of experimental kind of capability? It's because this is really what's going to be our magnifying glass for looking at the very, very small structure of nature. And I want to motivate why this very big thing is a magnifying glass. Okay, and I'll do this by using the tool that all of your physics teachers tell you to use, but you don't really believe them until it's too late, which is units. See, they're laughing, and you're laughing, but you don't get it yet. So you've learned from Einstein that E is equal to mc squared, that there's this relationship between energy and mass, okay? So that's good, that's important. In a certain sense, energy and mass are just different manifestations of the same stuff, whatever you want to call that stuff, doesn't matter, but energy and mass, same stuff-ish, okay? And for our use, I told you that there was these 13 TeV collisions. TeV is a measure of energy. One's useful for particle physicists and not useful for like blocks sliding down planes. But just to give you kind of an idea, the mass of the proton, which you may have learned at some point is a very small number of kilograms, is 1 GeV. And if you have 1,000 GeV, that's 1 TeV. Okay? So this is a giga electron volts, and the TeV is a tera electron volt. Just the same scales that you use for computer memory is happening here in electron volts. So you know about energy and mass being about the same, but what you might be less familiar with is the fact that energy is also related to the inverse of length. If you just take some fundamental constants, you can find out that, say, energy is related to the inverse of length in this way. And so there's a sense in which at higher and higher energy, we can probe details that are much smaller. The higher the energy, the smaller length scales we can get to. And you've kind of seen this before, perhaps, if you worry about, for instance, probing crystal structures. What do you use to probe crystal structures with? You can't use visible light. You use X-rays. X-rays have a smaller wavelength, and you can probe that structure using this higher energy, this smaller wavelength. So that's kind of the relationship that's going on. I will mention that throughout a lot of this talk, I'll probably drop all h bars and c's. They're just physical constants that are getting in the way of kind of seeing how these relationships work. So if you take c to be 1 and h bar to be 1, you see that energy is equal to mass, and length is equal to 1 over e. And that's kind of what we're looking for, that relationship. Okay? All right, so I told you the LHC is colliding things at 13 TeV, so that, roughly speaking, I'm saying the LHC can see things that are about 1 over 10,000 GeV, or about 1/10,000th the size, if you like, of a proton. Yes?
Okay, so I don't know what you mean by that. I mean, I can follow the math, but
Sure.
when you say you see the details, what kind of details? I mean, you're measuring measuring energies of particles, you're not measuring their size, so why do we care about this 10 to the minus 4?
Right, good. What am I probing? I'm not measuring the nature of protons, etc. Right. In a certain sense, I'm actually probing the vacuum. I'm probing what's there when nothing's there. The nature of nature, the stuff, the framework. So I'm trying to find out what is there at the bottom of things that gives me the rules for everything that comes up above that. In order to get that fine structure, I have to pump a lot of energy in.
Right, but you said you can see the details. What details? I mean, isn't the details like the energy of the particles that are made when you smash the stuff together?
I mean, those are details. Those are important, and we do that. But also, you want to probe the actual structure itself. So when I say something like the standard model, let's see, there we go. It's got all these pieces to it, which I didn't really introduce to you. These quarks, these leptons, different things having to do with forces. They're not just sitting there as, items in containers, like saying, this is my box and it has a gluon in it, etc. But there's these interactions. If you like, maybe this is a useful idea. If I had a very complicated set of masses and springs of different spring tensions or spring constants, kind of a very complicated meshing of all those. I want to find out not just what all the different kind of spring constants are, but I want to understand how they're all working together, what the whole modes of the whole framework are in a certain sense. So I want to understand all the pieces and how they work together. And in order to find out where the strings that are the stiffest exist, I have to really rock the system to make that stiff spring start to vibrate to see how it affects everybody else. Is that
Okay, well, I know about couple of constants, so yeah,
okay?
fine.
All right. I feel like I haven't satisfied you, but we'll see what happens as we go on. Feel free to interrupt me again.
Ellen.
Okay. Boom. Okay. So what do we see with, since we've talked about seeing things at the LHC? What are the big eyes? There are these detectors. And two that I'll talk most about today are the detectors of the ATLAS and CMS collaborations. Here's some schematics of them here. We won't talk much about the details, but just for scale, these things here are people. These are really big detectors. So they have this very narrow beam pipe coming through, and they're colliding particles together, and then stuff happens. And you want to measure all of that stuff in a very careful way, so you have these big detectors to catch all the stuff. Here we have my protons again, and they run into each other, and you see there's this flurry of stuff, garbage, going all over the place and lighting up different parts of the detector where some energy has been deposited. And here you might say the really interesting thing is that you have these two big deposits of energy, these big towers that are back to back. That might be the interesting part of the signal. That might be the important thing, to go back to that question from earlier. Okay, so that's part of the game. We also need to know what's tell new from old. So here I have some data for you. This is in a search looking for the Higgs boson, and they were looking for production of the Higgs, and it would sometimes decay into two what are called Z bosons. You don't need to know anything about them, but that's what's going on here, Higgs to two Z's, and then those Z's would go to four leptons, usually here the electrons or the electron's heavier older brother, the muon. Okay? And they'd find these four leptons, they have kind of where they went in the detector, and they would determine the mass of the thing that they came from. So the so-called invariant mass of these four leptons. And they're plotting that here. So how many events of that invariant mass get plotted. Okay? So this is one of the channels where they discovered the Higgs. Where is it? I'm showing it to you right here.
It's about 180, so it's like right around.
125.
5 points are right there.
Right here? Okay. So it would help if we knew what the standard model with, no, see, brave, thank you. See, just putting yourself out there. It would help if we knew what the standard model without a Higgs would predict here, right? So let's put in what we call the background. But besides the Higgs, what do we expect? Okay, so this is the background events. Now what looks like it's not aligned with the background?
125.
125, right? That part right there, of course. So
Could
we,
you go to that again? Could you go back?
can I go back? I can.
Jack, another one? Or is it good?
So bunch of stuff plus what we think we expect, and then something that looks unexpected. And of course you can make that, you make that much more precise with your statistical analysis, but this is just to go by eye that knowing what the backgrounds are is really important. And it kind of matters how you look for things depending on what kind of backgrounds there are. I will tell you that, for instance, the Higgs does not go to ZZ all that often, and Z's hardly ever go to leptons. But they looked here because it was such a clean signal that you could easily detect these leptons and find out what their mass was. And it could be, especially in a certain sense, a useful signal kind of in this window of mass. Yes?
Can I ask for a clarification on the background? The background then is events where you see 4 leptons.
Yep.
And the inferred parent energy from the distribution of the leptons. So the background is there are other cascades that lead to these 4 leptons.
That's right.
And so that had already been seen, and there was posited, well, even if you don't posit what the mass of the Higgs is, you plot the data and you see this bright signal of something new, some new physics.
That's right. That's right. So just if you take the standard model but take the Higgs out of it and say, I'm going to look for 4 lepton events with this type of invariant mass, what do the other players in the standard model say I'll probably see? And that's what this blue stuff is here. And then as you say, once I understand where that stuff is, if I see an excess somewhere else, or I see all these events where I expected only to see a few, then that's a strong signal.
Could I just follow?
Yep.
Like, I'm not familiar what these other particular peaks there are.
Sure.
There's another series of events.
Yep.
You know, at the around 200, what that peak is, or?
Yes. So as was pointed out here, this, you can tell the mass of the Higgs right here is at 125. This peak over here is actually producing just 1 Z boson. It has a mass of about 90. And here you're actually starting to produce 2 of them. But you're not producing, in a certain sense, one of them you're not producing it all the way. Let's say it's off shell, which may not be a useful bit of terminology for you. But that's kind of why you're getting this not a sharp peak, but kind of a smear over mass, I would say. But it's basically the point that you're getting 2 Z bosons just without having to go through a Higgs to get it. Yeah. Good. Any other questions? These are great. Thank you for asking them. Yes?
So how does the spectrum depend on the energy of the collision? You were talking about 13 TeV, and here you have like 7 or 8 TeVs. Any dependence on the...
Oh, right. So this is an old plot from when they were still colliding things at 7 and 8 TeV. There is some dependence, absolutely. What we would say the cross-section, your ability to make these different particles definitely changes. And that will go into how you simulate the background, certainly. And in fact, how you simulate the signal. So you have to do that all again for the different energies. Absolutely. Good eye, by the way. Good eye. Any other questions? All right. Oh, yeah. This wasn't about questions. This isn't about backgrounds. If I was to ask a question, and I was just going to say, everyone raise the hand you prefer to write with. You don't need to do it. But if I were, I'd probably just see a sea of hands. It'd be hard to say pick out the left-handers, because there's just a sea of hands. I mean, maybe if I'm looking carefully, I can see which side the thumb's on or something. But that's a question where there's a high background, and maybe that's not a useful one to ask. This is kind of already goes to the point I made about looking in this 4 lepton invariant mass, where it's kind of a clean signal. In fact, I looked in a very even more suppressed channel of the Higgs going to 2 photons, 2 kind of particles of light, which it only does maybe 1,000th of the time. But that was actually one of the discovery channels because it's so clean, just to see the 2 photons come out. Okay. Good. All right, so what are some of today's mysteries in particle physics? Some of them are, what are the neutrino masses, and where do those masses come from? What's their origin? Why is there more matter than antimatter? We're happy that there is. Here we are. But we can't actually explain that within the standard model of particle physics. What is dark matter? We can't, there's no dark matter in the standard model, so there's got to be something else out there. And then I had this very strange question at the bottom here, which is, why is the Higgs boson so light? Now, some of you are probably thinking to yourself, even before you raise your hands, let me anticipate you. Light compared to what? And second, who cares? I mean, it's a particle, I produced it, it has a mass, I measured it, I go home happy, right? So why do I say, why is it so light? What is going on here? In fact, I told you that it was, or someone mentioned it was 125 GeV. I told you a proton was about 1 GeV, so this is 125 times more massive than a proton. How is that light? It's heavier than almost everything else in the Standard Model. So to try to assuage your questions, which are good ones, let me kind of address them through a historical analogy. So walk with me down memory lane back to 1939, please. You remember Weisskopf. Of course. Remember classical electromagnetism, good old E&M, right? When you think of a proton, sorry, not a proton, an electron, you think of an electron, what do you think of? I mean, you often don't think of electrons, do you? Well, you should. A little tiny thing whizzing around, right?
Yeah.
But do you really think it's a point particle? And what does that mean, to be a point particle? It's probably a blob of stuff, right? Some kind of blob, some kind of structure, right? That seems to make sense. Well, it doesn't have. For me to model it, maybe, but I mean, really? No structure? That seems to ask a lot. I don't know about that. Let me just pretend that it has a little blob of, electrically charged stuff, but it's a little blob, so it looks like a point from where I am. Okay, well, if I make that assumption, then that means I have somehow got all of this negatively charged stuff to stay in a very small place, right? And you all know, because you've played with magnets, we've all played with magnets, right? Good. Those of you who aren't nodding should go home and play with magnets. This is important. If you try to put things that are the same charge close together, they push away, they repel. And so it takes a lot of energy to squash a lot of electrically negative stuff together, okay? And there's what we call a self-energy associated with that. You can calculate this if you want to. And you find that energy goes like, the electric, charge of that stuff, which I'll call E here, squared, over the radius of my, let's call it a sphere, right? Physicists are good with spheres. So I have some sphere of stuff, and this is kind of the energy that it takes to make sure, or that energy that's bound up in packing everything to that small space, okay? My model of the electron is a blob of stuff, okay? You'll notice that if I take R all the way to 0, say it's point-like, then this is actually an infinite energy, which maybe I'm uncomfortable with, the idea of infinite energy, okay? All right, well, that sounds fine. Let it not be 0. Let it be some number, sure. But see, there's this other issue, right? Einstein tells us that energy is related to mass. So if I've got all this energy tied up in this small space, that probably shouldn't be more energy correctly scaled than the mass of the electron, which we've measured. We know what the mass of the electron is, right? So if I'm going to say that the energy is somehow less than the mass, or mc squared, of the electron, then that means I'm saying that the radius of the electron should be bigger than this number here, which, let me just tell you, is putting in all the numbers, it's bigger than about 1 over 10 times the mass of the electron. So there's some scale where you would expect to see some kind of structure in the electron, okay? Only we've probed that structure and we haven't seen anything. It still looks very point-like, okay? So what's going on? Well, of course, electrons are these little wee particles, right? We're told very early that little wee particles have quantum mechanics going on, right? So maybe quantum mechanics comes in and saves the day. And in fact, you're right. Quantum mechanics does come in and save the day. So let's see how that works. You may remember, or perhaps you do not. Doesn't matter. I'm telling you now, and you can either believe or not.
That's good.
That's right. That quantum mechanically, especially, there's something about a particle's mass and kind of how it moves that somehow I'm sensitive to its mass. For instance, if I take two wave packets, if you like, two particles quantum mechanically, and I start them off in the same way in some configuration, and I let them evolve in time with some velocity, they look different later depending on what their mass is. How it's part of their dispersion relation, if those words are useful to you, okay? Relates to their mass. So there's something about particle traveling, particle dispersion that's related to their mass. That's all just to motivate the picture I'm about to show you, which is this picture. That you can actually calculate quantum mechanically these self-energy effects with these handy little pictures, so-called Feynman diagrams. And here's one of them that you need to incorporate, and you can see here this is somehow the electron interacting with itself, with the carrier of electromagnetism, which is the photon, which we label with a gamma. I really don't know why. So this is a self-energy effect. You can turn this picture into an actual calculation, into a number, or a formula, if you like, and you find out it has the same E squared over R behavior. So that's kind of good. We're reproducing our same classical intuition. It's positive. Of course, if that was the whole story, I haven't saved anything yet, so the problem is just as bad quantum mechanically as it was classically. But there's something that happens, right, at maybe twice the mass of the electron, at that energy scale. And what is that? Well, there's another particle. There's a new particle, the positron, that you don't hear as much about. It's just like the electron, has the same mass, but it has the opposite charge. So it's a positive charge guy. It's called the positron. And if you go to energies that are twice the electron mass, you can make an electron-positron pair out of pure energy. Okay? And so it turns out you have to include the effects of this positron, which I'll call schematically this way. You have the electron going along, and it kind of spontaneously somewhere else there was the production of an electron and a positron, and there's this annihilation of the electron and the positron, and this kind of correction from the self-energy. Okay? So we have to include this. We can't just include the one. And it turns out this also has the same E squared over R behavior, but crucially it has the opposite sign. So these two E squared over R behaviors cancel out. Okay? And it turns out the fact that the electron is what's called a fermion, that it has some intrinsic angular momentum or spin, is crucial to this cancellation, which will be important later. Yes?
Okay, so you're illustrating at the top right there before U to T
Yes.
that there's an electron, anti-electron, let's see,
Positron. Mhm.
collision, and they neutralize, and then it sinks down. So what happened? What's happening in that transition from to that lower point, and then the continuation? What is that continuation?
You're talking about this? Or,
Yeah. It's neutralized
Yep.
at that point there,
Uh-huh.
and then what happens in this falling transition?
This is just the photon interacting kind of in the same way that it did before here, this type of interaction. So it's just this self-energy type of...
So it's now a photon that's on the lower left here, going to the right?
The wiggly line is the photon. The electron is the guy with the arrows pointing this way.
Right, so how does it become an electron again?
This guy?
Yeah, it's now reemerged and continuing. How did that, what is that all about?
Well, so I will say two things, neither of which will satisfy you. But that's okay.
Just trying to learn something?
Yeah, no, and you should do that. Make me be accountable. I like it. But so part of it is these pictures are schematic. You shouldn't actually think of them as processes happening in time. They're actually a convenient way of organizing calculations, but a useful one. But if you forced me to interpret it this way, I would say that I have an electron going, traveling on, minding its own business.
Right.
At some time, because where time's going this way, I have the eruption of an electron-positron pair. That can happen. I've violated everything, so I have a positron coming out and I have an electron coming out. Okay? And that positron then intercepts this electron and annihilates.
I got all that.
Okay, then you got it.
No, but I don't understand
You understand this guy?
how what is resuming?
It's not resuming, it keeps going. This guy is where I started an electron-positron pair and it keeps going.
But if they annihilate each other, how come it's still going?
That's my question.
Right. So this electron and this electron are not the same electron. Yes.
I'd like to say that I read this
Yes.
as, in the vacuum of space, you could create electron-positron pairs
Sure.
virtually in a
Mhm.
moment.
Yep.
And so there's a period of time where you have your two electrons and a unusual, untenable, really. But now I'm showing you a method where out of nothingness, I can have a term which at the same time can cancel the e squared over r because my charge is negative, although it's e squared. Anyway, so I'm saying I may not be following you completely, but this diagram is a way to have this other sign thing, and it exists at the same time where you have an electron at the beginning, an electron at the end, and I can have a set of sort of virtual phenomenon happening which cancel the classical things that I think about. I don't know. Is anything close to it?
That is very close. I'll make it. It makes it sound like I'm a little bit too wishy-washy. I think where I'm just saying maybe this model works, but the thrust is exactly right. But it actually turns out that the positron's existence is guaranteed by the symmetries of special relativity. If you say I want to satisfy quantum mechanics and special relativity, I have to have a positron. And so at that level, this particle had to be there in a certain sense.
And when you're saying that, you don't mean just it needs to exist in our standard model. You're saying it needs to be something that we contemplate for every path of every electron.
That's right. That's right. If I have an electron, there is a positron. In a certain sense, they're not different. Yeah. Yes.
The caption is a new particle.
Right.
Okay. So this electron at the bottom, is that the new cell?
No, the new guy is this positron.
Okay. Now, okay, I'll ask you afterwards, because I don't get it.
That's okay.
I feel like I have it, but you're saying that's the logical step to say this putative other particle needs to exist to cancel this. I see where you're being more definite than I was.
Okay.
I got it.
All right.
But it's not the same electron at the bottom.
If you like. I mean, I'll go back to my first response where I say, this is just a schematic way of organizing a calculation.
I don't want it.
In a certain sense, it's the same electron, because you shouldn't trust this picture too much. But I'm giving a PowerPoint presentation, so I'm limited, right? You don't want to see the calculation. You really don't. So this is what we do, right? But I'm happy to talk. I'm creating feedback, so I'm gonna go over here. It's still going. Good. We've kind of already gotten to this based on your questions. That means I have a good class, right? That there's this power of symmetry that's coming into play. That if you say I need to have special relativity, if I believe in that, and I should because it's been experimentally verified, then there's a guarantee that there's this positron, and it comes in this way to cancel this most kind of stressful behavior, this 1 over r behavior. Now they don't completely cancel. There's a remaining effect. Which you can see here, but it's much milder. The dependence on the radius, if you like, is tied up in this logarithm. And so what does that mean? It means that when you have a bound on the radius of the electron, this is the bound, which ends up being that the radius has to be bigger than 1 over 10 to the 748 times the mass of the electron, which is pretty indistinguishable from bigger than 0, right? So even if I'm being persnickety and saying I think there's a little blob there, it can be really small, and I'm still not in tension with my understanding of physics in any way, right? As long as I'm keeping track of quantum mechanics and the symmetries of special relativity, the so-called Lorentz symmetry. Okay? Any other concerns? Because we're almost to the talk. This is all the intro, right? So, what is the lesson from the analogy? Okay. The electron's self-energy and this kind of divergent behavior was pointing us to some kind of new physics close to the mass of the electron. We said that by 1 over 10 times the mass of the electron, we should see something. And it could have been some kind of substructure. Maybe we would have really seen a blob, okay? But instead we find evidence of this symmetry, this Lorentz symmetry, the symmetry of special relativity that in some sense protects the mass of the electron from these corrections. In fact, there's this positron I have to account for. And the signal, if you like, of this symmetry is there's a partner to the electron, the positron, which is related to the electron by these symmetries. There's a certain sense where you take the electron, you act on it with the symmetries of special relativity, and you get the positron. They're related in this way. Okay? So this is all to tell you about the Higgs, right? That was what you came here to see, right? It was on the flyer. So what about the Higgs? The Higgs, crucially, to what I'll say here, is not a fermion. It doesn't have intrinsic spin or angular momentum like the electron does. It's a scalar, which means it has no intrinsic spin. Okay? It's a charged particle. It's charged under the weak nuclear force. It also has other couplings, interactions with particles in the standard model. And it has self-energy diagrams like we saw. And here's one here. And they kind of have the same behavior going like 1 over the radius of the Higgs, if we're thinking about Higgs substructure in some way. Okay? But because it's a scalar, it's not protected in the same way by special relativity that the fermions were. And I'm telling you now that the interaction with the top quark is in a certain sense most dangerous because it couples most strongly to the top quark. Okay? And it points then to energies close to 10 times the mass of the Higgs. Right? Which, remember, the Higgs was about 125 GeV, so this is something like 1,000 GeV, so 1 TeV, around there. Okay? That's the, yes?
Protected, am I right in thinking this comes from, well, the two plausibilities were, we were talking about spin with the electrons, but we were also talking about having an antimatter, having a symmetric antimatter particle, right? So basically you're saying it's not protected. Would I be better resting my thought process and saying the Higgs is not protected because there isn't an antimatter Higgs? Sometimes some of these particles, excuse me, I don't know, but some of them are their own antimatter particles and so on. So is that, what's the worst way of stating it's not protected?
Yeah, the Higgs is one of those particles. There's a sense in which every particle with even spin, or sorry, not even spin, but integer spin, is not protected in this way. So all the fermions, half integer spin particles, have this protection. There are other spin 1 particles, like the photon, but its mass turns out to be protected by the symmetry, so-called gauge symmetry of electromagnetism. And that's what keeps it massless. And in a similar way, the masses of the other force carriers, for the strong nuclear force, the weak nuclear force, are similarly protected. The Higgs, spin 0, it's not protected from the fermionic nature. It's also not protected by any gauge symmetry. And so it's just free. So we'll see how free it is. But so in a certain sense, it's uniquely in trouble in this regard. As far as it is its own antiparticle. That's right.
You can say what?
It is its own antiparticle.
A Higgs boson.
Yeah.
Wow.
Yeah.
And so that clearly isn't the rule for talking about the protection, right?
That's right.
The protection is, as you said, there were two. You gave us 2 ways: a gauge invariance or a spin.
That's right.
No. Yes.
Let's see. So the only kind of I guess the issue is spin is tied up with the Lorentz symmetry of nature, and so it is that's the sense in which a fermion having an antiparticle is guaranteed by the symmetry in a certain sense. So the spin story and the symmetry story are the same story. Yeah. Whether or not I've communicated that well in these slides. I apologize now and forever after for these slides.
Got my neurons firing.
Oh, good. All right. So what's going on with the Higgs? Maybe it's got substructure. Maybe it's made up of stuff, right? We know of particles like that, like the proton. We've talked a lot about. It's made up of stuff, made up of quarks. Maybe the Higgs is made up of stuff. Maybe there's 2 things inside of it that if we looked more carefully, we'd see that there's substructure. There's something about the Higgs which is stuff. And then we don't have this worry. We know how fermions work. I don't have to worry about the Higgs. In fact, we know of other scalar particles in the standard model that are composites of quarks, like the pions. You may have heard about them. They are scalars, but they're made of quarks. So we don't worry about their masses in this way, because fundamentally, they're made of these quarks. Okay? So then what is, because we made all these estimates related to energy, and I am never going to finish. This great. That we'd say then that the mass of the Higgs then would be related to the mass of its constituents, particle 1, particle 2 maybe, plus something to do with the binding energy. Okay? For instance, the mass of the proton, its mass is almost completely binding energy. Okay? That 1 GeV is not coming from the quarks. The quarks are a few MeV. So, like 1,000th of the mass of the proton. Everything else is this binding energy bit. So we might expect that also with the Higgs. Okay? So this is a great idea, right? Turns out it's disfavored by experiment. Okay? The Higgs is intimately related to the carriers of the weak nuclear force, and we've studied these very well at colliders. And basically, we should have seen kind of multipole moments associated with this substructure at these colliders after studying these guys very carefully, and we haven't seen them. Okay? So this is looking, I guess, under stress. You can kind of see that in this way with kind of the experimental bounds. If you remember the uncertainty principle, this is something from quantum mechanics saying that the uncertainty of a particle's momentum and position have to be greater than or equal to about 1. I put in a tilde there so you forget about the 1/2, and the h-bar has been set to 1. Okay? So go with me, tildes. So then if I want to estimate this binding energy, maybe a very, very rough estimate, okay, is that the binding energy is something like this uncertainty momentum, okay, which is then related by this to 1 over the radius. It's stuck. These particles are stuck in this radius here. Okay? That's the scale that sets them. So then experiment, this is an experimental bound, has bounded this radius to be greater than at least 1 over 50 times the mass of the Higgs. So I put in that experimental piece of data, and I put that into the formula from the last slide. I find that the mass of the Higgs is about mass 1 plus mass 2 plus 50 times the mass of the Higgs. This seems unlikely, right? So this is the tension. But you say what? Wait. What if there's some cancellation? I've made all these tildes, I'm just estimating things, right? What if there's some cancellation between like the kinetic energy of these guys and the binding energy of whatever's keeping them there, such that the total binding energy is only like the mass of the Higgs? Okay? That's certainly a logical possibility. Totally fine. But it's kind of weird, right? Why would the kinetic energy and the potential energy just happen to be the same so this cancellation happens? It could happen. I'll grant you that. But we call that a tuning of independent parameters.
But if it's its own antiparticle, then why wouldn't that be the perfect explanation?
I'm still not sure.
I'm just with language here now.
Yeah.
I'm not a physicist in any way.
Okay.
If Lynn is saying that the Higgs boson is his own antiparticle, right? You said yes, right?
It is.
Okay, then why wouldn't it be neutralizing in this way?
Well, I mean, so I'm not sure if I'm following you, but the antiparticle story still depended on the spin of the particle, the electron being spin 1/2, and the Higgs just isn't. It spins 0, and so that story just kind of doesn't work.
Too much beyond my...
Yeah. Sorry.
It's okay.
Okay.
I know you go on with it.
All right. And okay, so this tuning idea, though, it's fine, right? You can do it. It's not logically inconsistent. You can choose the parameters, say, of some composite Higgs model, a Higgs made up of stuff, such that the Higgs comes out to the mass we see, and you're still, satisfying experimental constraints. But hey, let's do better than that. If we're going to be tuning things, do we need to even say the Higgs is composite? Let me just say it's elementary, right? Then all I really need is like the radius to be really small, maybe 1 over the Planck scale, where I think things have to be different anyway, right? Maybe I can just do that. I'll just tune the standard model parameters such that happens, and I have a light Higgs. End of story, no mystery, right? Can I do that? Yes. But for this, I need a volunteer. Someone who's going to play nice. Anyone? All right, come on up to the front. Yes, give him a hand. I don't know who he is. You've never seen me before, right? So, okay.
All right.
I have here an American nickel. Please, check this nickel out. All right. Whoa. of the show. Okay. I'm gonna flip the nickel. You're gonna call how you think it's gonna land. We'll let it land on the floor. No funny business. Okay. All right. You give your best guess. Like if there's money riding on it. There's not. I don't have any money to give you. But as if there were. All right.
Okay.
Okay. Ready?
Yeah.
Okay.
Heads.
She called heads.
Oh.
It's tails. Oh. Okay. All right. Thank you. Good. All right. I'll note that you didn't guess edge. Why not? It's a logical possibility, right? It could have landed edge. This is a thing that could have happened. But for some reason, you didn't guess that. And in fact, the probability has been estimated by people who got published in PRE of the probability of an American nickel landing on edge. They said it's about 1 in 6,000, which seems ridiculous to me. Let's call it 1 in a million, all right? Just for estimation. I'm not saying they're wrong. I just haven't done the experiment, so I don't know. Suppose it had landed on edge. Would you have just said, how coincidental? How neat? What if it had landed on edge twice? Or 3 times? Yeah, that's right. Wouldn't you be suspicious? Let's say, if you tune the standard model Higgs to have the mass of 125, it's kind of like an American nickel landing on edge 6 times in a row. It's logically possible, but it makes you feel really uncomfortable about things, okay? And it's that uncomfortableness that we call not natural, okay? So we'd say, first, let's talk to Sherlock Holmes about this, because we seem to have a difference of opinion, because he says, when you've excluded the impossible, whatever remains, however improbable, must be the truth, right? And it's Benedict Cumberbatch, so I believe him. Okay? I agree. Well, let's fast forward in time, maybe 100 years, to another famous British detective, Dirk Gently. You guys know? Yes, good. He says, I reject that entirely. Okay? You haven't read your Douglas Adams. Okay. The impossible often has a kind of integrity to it that the merely improbable lacks. The impossible merely supposes there's something we don't know about. The improbable, however, runs contrary to something we do know about. We should therefore be very suspicious of it and all of its specious rationality. Okay? What's the point here? What's Dirk trying to get at? When you're working at the edge of understanding, it's really hard to say what's impossible. We're trying to figure out how stuff works. But we often can, with some confidence, exclude the improbable. That's not at the edge. We're saying, of the stuff we know, this seems very improbable. So the improbable and the impossible, or maybe the unknown, are on somewhat different footing. A light Higgs mass in the standard model isn't natural. It seems very improbable in some sense. It's hard to kind of make that rigorous and say, well, what kind of probability are you selecting from? That's a little bit, but it's very weird within the standard model for this very special value to be chosen. I don't have a reason for it. It seems non-generic in some way. A light composite Higgs is much more natural, but still a little bit uncomfortable. There's this order 50 tension that we have, which is much easier to deal with than the other. Yes?
Composite here means that it does have some
Yeah,
substructure.
that's right.
Not quarks, but maybe
Something like quarks. Yeah, there was this idea called technicolor instead of the color of normal quarks, and they were techniquarks, right? So, but yeah, something like that. Something else in fermions that made up this new particle. Okay, so the composite Higgs idea has been actively studied at the LHC, trying to see if we can see signals of this Higgs compositeness, and that should definitely keep going on, right? Because it's a totally good idea. Okay, what other possibilities are there? Well, we saw with the electron that if there was some symmetry, that might be a way of protecting the Higgs mass from these large corrections. You may have heard about supersymmetry. It's one of these ideas that there's this new symmetry called supersymmetry because it came out in the 70s and things were super. And there's these new particles called stops instead of top quarks. They're these stop quarks. What are S's going around? What? The quarks become squares. comes in later in the story. That's right. Well, all the scalars get the extra S. Some of the other guys get enos at the end. So you have a Higgs eno and a Weno. Let's just say that particle physics don't name things well, and move on. Well, quark was good? All right. Yes, that's right. Joyce, it's from Joyce, that's right. Like most of Joyce. Okay, so that supersymmetry is not the only option. You can have so-called little Higgs models. There's a different kind of symmetry, but there are then partners to the top quark that come in. They can be fermionic partners. Here in supersymmetry, there were scalar particles. These are going to be fermionic partners that protect the Higgs mass. But we should see, right, these evidence of these top partners by 10 times the mass of the Higgs, or else we're back to our issue of tuning and not knowing why there's this hierarchy between these scales. Okay, a lot of options out there. Now I'll bring you to the top partner folk theorem. Clearly, I don't treat it with much. Anyway, the top quark carries a certain kind of charge. So because particle physics don't name things well, it's called color. Right? This is what keeps things like the proton bound together. Okay? And neutrons. This strong nuclear force, this color force. The top quark carries these things. So then the symmetry partners, just in the same way that the symmetry partner of the electron had electric charge, the symmetry partners of the top quark should have this color charge. The LHC, what does it do? It takes protons, which are like big garbage bags full of color. They really are. And it smashes them together. So you should be able to really produce these quite copiously these top partners. Okay? Unless they're too heavy, but then we're back into this tuning regime that we're uncomfortable with. So that was the idea. So, in the context then of our detector story, what happens? We build the LHC, we start ramming protons together, we rush to the scene of the protection of the Higgs mass, hoping to see these new partners. And what do we see? A whole lot of nothing, actually. The LHC has run very well, experimentally, phenomenally well, better than expectations, and they've put very, very good limits on the masses of these partners. Very, very, including a bunch of places that are very hard to look for when using it. We've become very good at looking for these symmetry partners. As of yet, there's been no sign, no hint of these symmetry partners. That's too bad. I was really excited about this topic until this point, right? Where are we going with this? The unnatural Higgs mass descending model is not a striking signal of new physics in the sense of like a bump in the data, right? It's not like footprints under the window, smoking gun. It's a lot more like the curious incident of the dog in the nighttime, which you may or may not remember. But there was a case where Watson and Holmes were investigating, I believe, theft. And as they were learning more about it, Holmes was looking very sure of himself. I've kind of got this figured out. And Watson's like, we haven't learned anything. So Watson says, is there any point to which you wish to draw my attention? And Holmes says, to the curious incident of the dog in the nighttime. The dog did nothing in the night. That was the curious incident. In this case, because the dog made no noise, must have known, the thief who came through, right? There must have been some knowledge. And so, how do I relate this to the story I'm telling you here? Which is there anything I want to draw to your attention about these new particles that attack the mass of the Higgs? Well, they have a very curious nature, don't they? Well, we've seen no new particles that protect the Higgs mass. Yeah, that's interesting. Oh, I haven't seen them. Why? That's telling us something about them. If I believe they're there, or that there's a good chance they could be there, I have to somehow, they have to accord with this experimental fact that we haven't seen them. Okay? Which is different than saying that they're not there, right? A little bit different, just a little bit. So this brings up the idea of colorless top partners, which in my last little bit of time. I'll tell you about the work I've done on colorless top partner models. But these are exactly what you might think. These are ways of explaining the light Higgs mass using new symmetries, but these new symmetries behave in such a way that the partner particles, the symmetry partners of the top quark, are not charged in standard model color. There's a bunch of different names for these guys. The first of these is called the twin Higgs, and there's voltage supersymmetry and the quirky little Higgs. Great names, right? And their details are not important for our discussion here, but that there's this kind of this wealth of knowledge. What shall we say? Because they're not colored, they're hard to find in the LHC, but they have to talk to the Higgs. So the Higgs is a very useful probe of these types of fields. Because their whole point is to couple strongly to the Higgs and protect it in some sense from these large directions.
Say that last sentence.
The whole point of these top partners is to couple strongly enough to the Higgs, just as strongly as the top quark does, in order to kind of cancel the effect of the top quark. So I can use the Higgs, or I should be able to use the Higgs, as a probe of these new guys, even if I can't produce them directly at the LHC very effectively. I should be able to use the Higgs, this newfound particle, to get at their nature to some extent. There are some ways to do that when you go fast.
Right now, put that one down.
Put that one down. How can we do that? We can look at the couplings of the Higgs, the standard model fields. These are all predicted within the standard model. If we see deviations of these couplings, that's a hint of something new is going on. If we can relate those coupling deviations to these new frameworks, that could be a sign. Agree with that. There could be so-called exotic decays of the Higgs. You know how the Higgs decays. It doesn't last very long. It's a very short lifetime. And its predictions into, its decays into standard model particles are all known and predicted from the standard model. If there are decays into new particles, new things, even if we don't see them, we can see the difference in the Higgs width and the way that it's behaving. It's a signal of these exotic decays of the Higgs. That could be a sign about these new guys. These all have their challenges, but they're worth exploring, which is what myself and some collaborators have done. So don't try to understand this plot, but let me just tell you that it's telling you about how well you can constrain models like the twin Higgs using Higgs coupling deviations and how well they've been studied so far at the LHC and how precisely they're likely to be studied at the LHC. So even just constraining how standard model like Higgs couplings are so far, you can put a bound on the mass of the twin top, this top partner, already beyond 600 G. But you can't get much better probably, well, sorry, this is how well you will be able to do by the end of the LHC run. Right now you're closer to here, around 400 G. Okay? Or I put it in Higgs masses for you.
Could you repeat that? You said right now we're at 400 and you think that the top capability of LHC will be where?
That's right.
Where would I think the top right there?
This is the top capability, is saying kind of this close to 1. If this got to 1, it would be standard model-like couplings. And so as we get closer and closer to 1, that's more and more standard model-like. But the LHC is not going to get better to about 0.9, is what I'm saying. And so there's a limit to how precisely it can probe. And so in that sense, how far it can reach in the mass of these new partners. And this idea, this twin Higgs mechanism. In fact, for other ideas, the so-called folded SUSY, it can only reach a very, very small amount for precision Higgs couplings. And I see that we're out of time. The bouncer is coming. You can do lots of other fun things with plots and exotic Higgs decays using displaced vertices, which are really cool.
Oh, sure.
Yes?
I know you got 1 minute, but that's a plot I wanted to see. That looks this is experimental, obviously, but
Actually, this is not. This is
no, the draw,
this one.
you're showing us the experiment, right? The calorimeter and
Yes,
so
this is
on.
a cross-section of the SDSM.
Okay. And then, can you tell us about?
So displaced decays are nice. If I'm looking for an exotic decay of the Higgs, where the decay leads to a displaced signal, this can be useful because even if I only get a small number of events, which I'd like to get in an exotic decay, the backgrounds are much lower for these displaced signals. Instead of seeing things happening right here at the interaction point in the tracker, if I see the action happening a lot later, or even displaced in the tracker.
And you really mean displaced on, along the z-axis of the beam line, or off the
Off-axis.
Off-axis.
Off-axis. nothing and then suddenly stuff happening. That's a more striking signal, much lower background, and even with many fewer events, you can start, oops, wrong way, you can start setting pretty interesting bounds, potentially to LHC, even reaching up to maybe 8 times the mass of the Higgs in some of these models. That's the idea there. There's other things you can do. Let me end. Okay? That things are getting interesting or are still interesting. This puzzle, the jury is still out as far as a natural Higgs mass. The bounds are being pushed further and further at the LHC, whether with compositeness, whether with symmetry partners. We don't know what nature is doing, but we're trying to explore all possibilities as best we can. We need lots of imagination and novelty to keep up with what nature might choose to do. But my invitation is for you to just keep reading, because I think we're still getting to the interesting part. Thanks.
Leptons and towels and bosons, oh my. Thank you very much for that talk. As we're at 5 o'clock, those of you who are here for extra credit, you're free to depart as quickly and quietly as you can. And those of us taking it for credit or otherwise are welcome to remain behind, and we'll take questions on that. Just a quick notice that our speaker will be staying for dinner, so if you'd like to join us tonight, come and see me at the end, and you're welcome to do so. Do you have any questions for us, Scott?
Yeah, I guess the conundrum that's lighter than we expected. How should I have that in my head with the same idea that we thought with the LHC we find the Higgs? Am I missing something? Like, was it really sold on an idea of being in a place where it couldn't have been, or?
No. We're still dealing with this issue in the sense of the LHC was built on a promise, and that promise has been fulfilled.
Yeah.
And it was really ironclad. But now, if you look into the next stage, people want the same level of promise. We have nothing to give them. It was really a rare event that we can say you need something like the Higgs, or else the standard model doesn't make any sense at all. You actually have cross sections, processes happening that would be growing without bound, based on all the particles we've seen both out of Higgs boson.
So there were existing limits on it, and what you're saying is those existing limits put by other experiments still had this conundrum that it led to a mass that was well defined of what it should be, but at the same level, it's not a natural thing for it to be that mass.
That's right, and that's why people thought, well, you won't just find Higgs, you'll find supersymmetry, or you'll find these top partners, because they expect them to be nearby. So this was, because, yeah, they knew about this naturalness problem, a long time ago, at least back in the early 80s. They said, well, maybe this elementary Higgs radius isn't such a good idea, because it has this issue that it's sensitive at these very high scales. So they thought a lot about, what could save the day there. First, probably just composites. Probably the Higgs is just some composite. It doesn't have to be elementary. It does all the same job as the Higgs. Investigating these ideas, but even precision measurements long before the LHC, we're putting that in tension. These measurements of, like I said, the measurements of the W and Z bosons, the weak force carriers. So yeah, this was already this has been motivating the field of elementary particle theory for decades, and we thought we'd know by now, but here we are. Yeah.
So, does that mean you have to build another accelerator? Because, the LHC is sort of running at its top energy, so.
We always have to build another.
Is the ILC or anything that ideas that people can build, and they can be able to get in any of this any better?
So the ILC is nice in the fact that it can do precision Higgs measurements, right? So where I showed you the gap between 0.9 and 1, the ILC can push that in at least some couplings to well within, greater than 0.99. So you're getting much more precise measurements of Higgs couplings, which could be a signal of many kinds of new physics, beyond this issue. Higgs is kind of special in the way that it can couple to things for reasons which are technical, but if you really want to know, you can later. But so that's to me, that's the most motivating thing about the ILC, is that it can do this precision Higgs measurement stuff. The thing that's less exciting is it's a very low mass. It can't go to higher energies like LHC does, and so it'd be nice to have a different machine that can None of these are cheap, obviously. But I would hesitate to give any guarantees because unlike there has to be a Higgs, which was at the level of a relative theory really doesn't make sense. This is more like, I mean, the theory is still self-consistent. It's just there's this weird apparent tuning, and there could be other reasons for that. It's a matter of kind of, I've heard it said like, how do you want to gamble? You know, is this a strong motivation for new physics? I say yes, but I can't point you to where it's going to show up. So you probably want to find a new machine that can hopefully address this, but also address things like dark matter, very honest imagery, and neutrino masses. See as much as you can get with the same machine. Yeah.
So I'm an astrophysicist by trade. That's why supersymmetry.
So are you going to ask?
Astrophysicist by trade. So I don't know as much on the supersymmetry, but I found it interesting that we have the cosmic particle accelerators, right? We basically have higher energy events than we can produce here on the ground. I haven't done the calculations, but obviously a base on the moon, you could have an atlas. I don't know whether you would get enough rates from these more spurious or stochastic events. But is there any thought in particle physics, and certainly Dr. Kaminsky has worked on experiments which are like particle physics experiments in space, but on the scale of colliders and looking at new energies, are people thinking 30 years out and places on the moon?
I don't know about the moon. That's another layer of expense. They are thinking 30 years out about current machines. I've participated in some kind of working groups or meetings where we're trying to make projections. What can we do if we take the LHC and take some new magnet technology at the same tunnel, which is not the biggest expense, put in new magnets, how much more energy can we get into it? If we have a much longer run with higher luminosity, can we find things that are more rare? So these are the questions that are being asked. Or should we just build a much bigger collider, the same type of idea, but much bigger, so we get to much higher energies? People are trying to figure that out and figure out the costs and figure out what makes sense. I also know this is related, but not. I mean, there's already a fair amount of work that has been done and is going on with kind of cosmic rays.
And then air shower
And air
experiments, sure.
You have much less control over the initial state, obviously, and so much of this is going with kind of what do I expect? What do I see is different from what I expect? And I think there's maybe a lot more unknowns. I mean, we'd love to. I mean, I think the positron was found in cosmic rays, right? So certainly the possibility is out there. We'll see something we've never seen, and that'll tell us what machine to build to test it. But I mean, so that's ongoing, and I think it should keep going. But I think there is you lose a handle on being able to kind of control what's coming in. It's pretty detrimental to precision. Yes.
I think we're actually running just a little bit low on time, so let's wrap up